Hi, this is John Whitaker for the Mathematical Analysis 1 class, and this is our 13th video lecture. And last time we ended with a theorem about unions of open sets and intersections of closed sets, and we had done the first part of this theorem, but it had 4 parts, I believe. So let's re-examine that theorem and prove the rest of the parts. Okay, so here was the theorem. It said for any collection G sub alpha, and this is part A, of open sets the union of the G sub alphas, alpha element of A, an indexing set, is open. That's part A. Part B was that for any collection let's call the script F equal to, I'll call this big F sub alpha, that's that alpha is the element of A, of closed sets then the intersection of the F sub alpha, this alpha is an element of A, is closed. Part C, if, or it says for any finite collection of open sets G1, G2, up to Gn, then the intersection of the GIs, here I runs from 1 to n, is open. So here I want to, open. Let's finish up the statement here. In part D, for any finite collection closed sets F1, F2, Fn. Then the union of the Fn, or F sub I, as I run from 1 to n, is closed. Okay. So for the proof, part A we did. Part B, okay, we're going to let F sub alpha, since alpha is an element of A, an indexing set, be a collection of closed sets. And what we want to do is we want to show that the intersection of the F sub alpha is closed. So what we want to do that is show that the complement is open. So, since f sub alpha is closed for every alpha element of A, then f sub alpha complement is open. So the union of all alphas element of A of f sub alpha, that's open by part A. Okay. And so since that's open, I'm sorry, I made a mistake. Here this should have complement. Okay. So f sub alpha is closed. So that means f sub alpha complement is open. So if these are all open, when we union them up, we get an open set. Okay, that's fine. And so, by a previous fact, if we take this union and look at its complement, that is closed. Say by a previous fact. Now, let's look at this set. Note the union of all alphas in A of f sub alpha complement. What that's equal to is the intersection of all f sub A complements, as alpha is an element of A. And f sub alpha complement, just this part right here. Okay, that way. That's just going to be equal to f sub alpha. Okay? But what do we know about this set that's closed? Okay? So that means this intersection is closed. And that's the proof of part B. Okay, so for part C, we let G sub 1, G sub 2, all the way up to G sub n be a collection of open sets. We want to show that their intersection is open. And so we're going to do this directly from the definition of what it means to be an open set. And what it means for a set to be open is every point in that set is an interior point of that set. So this is what we want to show. Okay. So we're going to start off with let X be an element of this intersection. Then, what does it mean to be in the intersection? It means that it's an element of each set. So then X is an element of G sub I, and that's true for all I equal 1, 2, 3, all the way up to n. Okay. Since each Gi is open, that means there exists an R, we'll say R sub I, such that the neighborhood about X with radius R sub I is going to be contained in G sub I. Now, what we're going to do is we're going to let R equal to the minimum of R sub 1, R sub 2, all the way up to R sub n. So the minimum of these radius values. Then the neighborhood centered at x with radius r, okay, is going to be contained in G sub I for all I equals 1, 2, all the way up to n. So since this neighborhood of radius r about x is in each G sub I, or is a subset of each G sub I, then is going to be a subset of the intersections of the G sub I. So here we have shown that x is an interior point of this intersection, and x was an arbitrary element of that intersection. So that means that everything in that intersection is an interior point of that intersection. So that says that this intersection is open. That is part C. For part D, we're going to let f sub 1, f sub 2, up to f sub n be a collection of closed sets. We want to show that the union, psi runs from 1 to n of f sub I, is closed. So we're going to do this with complements here. Okay, so we should note that f sub I complement is open since f sub I is closed. Okay? So, by the previous fact, the finite intersection, as I run from 1 to n, of f sub I complement, that's going to be, is open. And so its complement is going to be closed. But before I say it, does this finite intersection of the complement here, this could be thought of as the union of f sub I complement is open. That's true. That's because these two sets are exactly the same. Thus, this union, I went from 1 to n, of f sub I, take its complement, is closed. And that gives us that the union of the i's running from 1 to n of f sub I is closed. is because these two sets, the union of the f sub i's, if you take its complement and then take its complement, that's equal to the union of the f sub i's. So that proves that part. Now, I'd like to look at an example of why we can't extend this last result. The last result was saying that if you have, well, it wasn't the last result I'm going to extend, it's the next to last result. What it said, the part C, it said that if you have a finite collection of open sets, if you intersect them, then that's going to be open. But why can't we just intersect an infinite collection of open sets and get something that's open? Here's a counterexample of that. So notice this example. If we look at the intersection as I run from 1 to infinity of the open set minus 1 over n up to 1 over n in the real number system, that equals to the collection 0. And that's the set containing 0. And so here, we're intersecting a bunch of open sets. But since we have infinitely many that we're intersecting, what we get is not open. This is closed in this case. That's an example that shows that we can't just say that the intersection of any arbitrary intersection of open sets is open. It could be closed. And likewise, we could not say that the union of any collection of closed sets is closed. There are kind of examples of that. But we can say it for finiteness. Okay. The next thing we'll do is look at the definition. It says if X is a metric space, and E is a subset of X, and we're going to say E prime denotes the set of all limit points of E and X, then the closures, here's what we're defining. The closure of E, denoted by it's E with a bar over it, is given by, so E closure is equal to, it's equal to E union all of its limit points. That's the definition. Next thing I want to do is say a fact, or say several facts about E closure. We'll wrap it up in one theorem here, but theorem has several parts. It says if X is a metric space, and E is a subset of X, then first thing is that E closure is closed. The second thing is that E equals to its closure if and only if E is closed. And thirdly, the closure of E is contained in F for every closed subset of X that, let's say it's every closed subset F that contains E. Okay, so what we're saying is E is closed. E closure is a closed set. And as a matter of fact, E itself is closed if and only if it's equal to its closure. And E closure is really the smallest closed set that contains E. That's what these three things are saying. We'll prove them. Okay, so for part A, we want to show E closure is closed. Okay. And the way that we're going to do that is show that its complement is open. Okay. So here we let P be an element of X with P not being an element of E closure. So how can that be? Well, that means that P, because of the definition of E closure, isn't an element of E, and P is not an element of the limit points of E. Not an element. So let me write that out. Is not a limit point of E. So what does it mean for P not to be a limit point of E? That means there exists a neighborhood, let's say N sub R of P, such that N sub R of P does not contain any point of E, okay? And P is not in E, so that means that N sub R of P is contained in E complement. So N sub R of P, for it not to be a limit point, means that it doesn't have any intersection with E besides possibly P, but P is not in E either, so it means this whole neighborhood has to be an E complement. Okay. All right. Now we let Q be a limit point of E. Now, here's what we claim. We claim is that Q is not an element of N sub R of P. So what I'm thinking is this particular subset cannot contain an element that's a limit point of P. Now we're going to prove this one. So proof of claim. I'll put this in parentheses. We're going to do it by contradiction. Let's say suppose Q was an element of this neighborhood of P. Now, we know every neighborhood of Q contains a non-Q element of E. We know that because that's what it means to be a limit point. Okay, so since Q is an element of this neighborhood, and this neighborhood is open, then there exists an n sub r not Q, so this is a neighborhood of Q, such that, so Q has to be an interior point of this set, since this set is open, okay, this neighborhood is open. And so that means that there exists this radius for this neighborhood of Q, such that n sub r naught of Q is contained in n sub r p, but we know this guy is in E complement. Okay, E complement is where it is. Okay. So that says that n sub r q is contained in E complement. Okay. And remember, n sub r of q is supposed to have something, or n sub r naught of q is what I should say. N sub r naught of q is supposed to contain some element that's in E that's not q, but that's not possible if this neighborhood is contained in the complement. It can't contain something in E. Okay, okay. So that proves the claim. Here I'll say n's proof of claim. I'll put that in parentheses. So what we've got is if you give me a limit point of E, it can't be in this neighborhood. Okay, so what does that tell us about that neighborhood n sub r of P? Well, we know it's contained in E complement, and none of its points are limit points. Okay, can't contain limit points, so none of its points are limit points. So it's contained in E prime complement, the limit points of E. So what does that say? So n sub r of P is a subset of E complement intersected E prime complement. That's what it says. And what does that mean? So that says so that n sub r of P is contained into E union E prime complement. And that was exactly closure of E. So this says n sub r p is contained in E closure complement. Okay. Thus, that says that P is an interior point. Of E closure closure complement. And so P was just an arbitrary point in this E closure complement. So let me write that down. And it must be interior point. That means every point of E closure complement is an interior point. That says this E closure complement is open. And so that gives us the first result that E closure must be closed. Let me write that down. Because its complement is open. So that proves part A. Okay. For part B, we had two things we wanted to show. We want to show, so let me write that. We want to show E equals to its closure if and only if E is closed. That's a recollection of the statement. So we've got two directions here to prove. So suppose E does equal to E closure. Okay? All right. Well, it's very simple. Since E closure is closed, then E is closed. So that's the one direction. And so if it's equal to its closure, it's got to be closed because its closure is closed. Backwards direction, if E is closed, what we want to do is show that it's equal to its closure. Okay? But if E is closed, what does it mean to be closed? It means that it contains all of its limit points. Okay. So what that means is that as we denoted its limit point by E prime, that's contained in E. So that means that E is equal to its self-union with its limit points. Its limit points are contained in E, so when you take E and combine it with its limit points, well, you're not adding anything new, it's just E. Okay? Thus, that's E closure, so E equals to E closure. So that's that proof. That's pretty quick. Okay, we still have part C to do. So in part C, let's don't forget what we're trying to do. For part C, we want to show that E closure is a subset of every closed set that contains E. That's what we want to do. So let's let F be a closed set that contains E. We want to show that E closure is contained in F. Now, since F is closed, F contains all its limit points. So we want to make sure that it contains all the limit points of E. So we let P be a limit point of E. What does that mean? Then every neighborhood of P has a non-P point of E. And that's what it means to be, for P to be a limit point of E. Since E is contained in F, okay, then every neighborhood of P contains or has a non-P point of F. Okay. Okay. So that means that P is a limit point of F. We're in the wrong thing. Okay. Okay. And thus, P is an element of F as F is closed. So we can say, all the limit points of E are in F. Okay? That is, we're saying these limit points are a subset of F. Write that in parentheses. Since E is equal to, E closure is equal to E union its limit points, and E is a subset of F, and the limit points of B is a subset of F, then E closure is a subset of F. That's what we wanted to do. Okay, here I'm just going to parentheses say, well, look, if one set's contained in F and another set's contained in F, if you union them up, that set's contained in F. So if we let X be an element of B closure, so I'm just going to go over that with you right here. Then X is an element of E, or X is an element of the limit points of E. If X is an element of E, then X is an element of F. So we only have two options. If X is in E, then X has to be in F, as E is a subset of F. If, on the other case, is if X is an element of the limit points of E, then X is an element of F as the limit points of E contained in F. Hopefully that's helpful. Okay, well, there's at least one more theorem I'd like to get up. Improvement. What is this proof? Here's a theorem. It says let E be a non-empty set of real numbers which is bounded above. Let y equal to the supremum of E then y is going to be equal to the closure of E. Hence, y is an element of E if E is closed. And this is a statement about subsets of real numbers. Let's look at its proof. Let's first of all work on the existence of y, the supremum of E. So note, since E is a subset of real numbers that is bounded above, then the sup of E exists as a real number as the set of real numbers R has the LUB property. Okay, so we look at two cases. Remember, what we're trying to do is we're going to try to show that y is in the element of the closure B. Now, case 1, if y is an element of E, then y is an element of E closure, as E closure is equal to E union its limit points. Okay, so case 1, that's good. Case 2, we're going to suppose that y, the supremum, I should have written that here. So let's let y equal to the sup of E. Okay, that's what I mean by y. Okay, if y is not in E, then what we got to show is y is a limit point of E. So we must show y is a limit point of E. Okay, to do that, we must show that to be a limit point, we have to show that every neighborhood of y contains some point that it is not y of E. And of course, that means it just contains, that neighborhood contains some point of E, okay? Because y isn't in there. So we let r be greater than 0. Then y minus r is going to be less than y. That's sure. Okay. So, this guy is a real number that's less than y, and y is the supremum of E. So that means that y minus r is not an upper bound of E. So that means there exists an x, let's say, that's an element of E such that y minus r is less than this x, and it's going to be strictly less than y. And the reason it's strictly less than y is because x is in E and y is not. Okay, so it can't be equal to y. Thus, for every r greater than 0, n sub r of y contains a point of E, this guy x, okay? Contains a point of E. It contains a point of E, these neighborhoods do, that is not y. So that says y is a limit point of E. Thus, y is an element of E closure. Okay, there was a secondary statement associated with this theorem, and that is if E is closed, okay, we want to show that y is in E, the supremum, then by the previous fact, E is equal to E closure. So if y, so
So if, E is closed, we just showed that the spring room has to be in E closure, so it's got to be in E. And that's the proof.
Ladies and gentlemen, that's enough for today.